Hello, everyone. Starting from this video, we will relate the actuarial functions of the mortality models with the life table. A table given in the SOA exam looks like this. We only need the first three columns in this section. From this, you can see that the life table provides information regarding the mortality of individuals at integral ages. For example, an individual at age 21, we have QX. Q21 is 0.000253. A life table begins with the number of independent lives at an initial age x0, and the corresponding number of independent lives at this age 0 is Lx0. In this table, x0 is 20, and we have L20 equals 100,000. And this is the base of the group we are working with. This is called a radix. We have a radix of 100,000 at age 20. And at later ages, Lx denotes the expected number of survivors at age x. Let's define more notations. Suppose we have a radix at age x, age 0, we have L0 alive, so that is L0 number of newborn at age 0. And then within this, the first year, it is expected that, say, D0 number of deaths. By age 1, by the end of the first year, only L1 life remains, L1 survivors. We can link up the three quantities L0, L1, and D0 by this expression L1 equals L0 minus D0. Starting with the number of survivors at age 0, which is L0, and then less the number of deaths, which is D0 in this year, and we get the expected number of survivors reaching age 1. Similarly, in the next year, expected number of deaths is D1. So by age 2, only L2 number of survivors. We have L2 equals L1 minus D1. The general expression, we have Lx plus 1 equals Lx minus Dx. More definitions and relationships. All right, so we have Dx equals Lx minus Lx plus 1, and Dx is the expected number of deaths between ages x and x plus 1. And we have a notation n dx. This is the expected number of deaths between ages x and x plus n. The number of deaths within n years after reaching age x. And this equals dx plus 1 plus up to dx plus n minus 1. From the L's and the D's, we can calculate the survival probability or the mortality probability. For example, Px. Px is the probability that an individual at age x can survive beyond age x plus 1. This equals Lx plus 1 over Lx. Lx plus 1 is the expected number of survivors reaching age x plus 1. And then Lx is the expected number of survivors at age x. So that is out of Lx number of survivors, only Lx plus 1 number of people survive or reaching age x plus 1. So this is Px. For Qx, this is dx over Lx. The number of deaths within the first year after reaching age x over the total number of survivors at age x. Qx is 1 minus Px, or dx is Lx minus Lx plus 1. So we can express Qx as Lx minus Lx plus 1 all over Lx. From that, we can also get an expression for Tpx, which is Lx plus T over Lx. And TQx is T dx over Lx, which is Lx minus Lx plus T over Lx. The deferred mortality probability, U bar TQx, an individual currently at age X can live beyond X plus U, but dies before reaching age X plus U plus T. And this is the expression for this deferred mortality. All right, so let's take a look at an example. Get familiar with the expression, the entries in the life table. All right, so we are given a life table. We only need the value of X, the age, and the number of survivors, Lx, and then we can get somehow say the dx and calculate the survival as well as the mortality probabilities. All right, let's compute the dx column. The first one is D80, the expected number of deaths for an individual at age 80 will die before reaching age 81. From the table, at age 80, the expected number of survivors is 400. And then at age 81, the expected number of survivors is 232. We can deduce the number of deaths. This is L80 minus L81. 400 minus 232, we get 168. And then D81, 232 survivors at age 81 and 128 survivors at age 82. The number of deaths between the ages 81 and 82 is 104. Similarly, D82, we get 62, and D83, we get 34. The next quantity we want to get is L85, the expected number of survivors at age 85. We have L84 is 32, and the expected number of deaths within this year is 18. Therefore, L85 is 32 minus 18, which is 14. All right, and then the probability 2p81. An individual currently at age 81 survived beyond age 83. From the life table, there are 232 survivors at age 81, and then until 83, there are only 66. 66 out of 232 people survive, reaching age 83. So this is L83 over L81, and we get the probability 0.2845. How about Q83? 66 survivors at age 83, and there are 34 number of deaths within this year before reaching age 84. And this is Q83. So we get the probability, which is D83 over L83. We get 0.5152. D80. So this is L80 minus L83. The expected number of deaths within 3 years, given that the individual age is currently 80. That is, an individual currently at age 80 will die before reaching age 83. So the corresponding number of deaths, L80 minus L83, which is 334. The number of deaths at between age 80 and 81, the number of deaths between 81 and 82, and then the number of deaths between age 82 and 83, sum them up. And then the last quantity, 1 bar 2 Q80. An individual currently at age 80 survived beyond age 81 but died before reaching age 83. All right, so from the life table, 400 survivors at age 80, and out of this, 232 can survive to age 81, and then only 66 can survive up to age 83. To get this probability, which is L81 minus L83 over L80. And this is 0.415. Let's take a look at another example. Given that S0 is 1 minus x squared over 100 and L0 is 1000, calculate L4, L5, D5, and 2D7. All right, L4, from the relationship TPX equals Lx plus T over Lx, and we get the relationship Lx plus T equals Lx times TPX, and we want to get L4, and we are given S0. So L4 is L0 times 4P0, and 4P0 is in fact S0 of 4. Substitute x equals 4 in S0, and then we get L4, L4 equals 840. And then L5, L5 is L0 times 5P0, which is L0 times S0 of 5. Upon calculation, we get L5 is 750. To get D5, the number of deaths between age 5 and 6, which is L5 minus L6. We already obtained L5, which is 750, and then L6 is L0 times S0 of 6. We get D5 equals 110. And then the last quantity, 2D7, the expected number of deaths between age 7 and age 9, which is L7 minus L9. L7 is L0 times S0 of 7, and L9 is L0 times S0 of 9. We get this expression, and then substitute x equals 7 and x equals 9 respectively. And we get 2D7 is 320. All right, let's get back to the notation Lx plus T. This is the expected number of survivors at age x plus T from Lx independent life at age x. If Lx is an integer and denotes the number of survivors survive to age x plus T as a random variable, Lxt, then Lxt follows a binomial distribution with n equals Lx, and the probability of success of the binomial distribution is TPX, the survival probability. And we can get the expected value of Lxt, which is Lx plus T. So this is the expected number of survivors reaching age x plus T. And we can also get the variance. Lx times Tpx times 1 minus Tpx. Which is Lx times Tpx times Tqx. We can also express any quantities like dx. Dx be the random variable, okay, representing the number of deaths between hx and hx plus 1 from Lx independent life currently at hx. Dx also follows a binomial distribution. The binomial distribution with n equals Lx, and the probability of success in the binomial distribution is the Qx, the 1 year period mortality probability at hx. And therefore, the expected value of dx is Lx times Qx, which is dx. And the corresponding variance is Lx times Qx times Px. All right, let's take a look at an example. Given that the force of mortality mu x equals 0.001 times the square root of x for all x, suppose we have a notation L20. L20 to be the random variable denoting the number of lives alive at the end of 20 years. And suppose there are 5,000 lives at age 30 by time 0. Calculate the expected value of L20 and the variance of L20. All right, originally in the previous slide, we defined the symbol as LXT. So here in this question, it is defined as only L20. And in fact, from the context of the problem, we are considering the notation as L30, 20. The current age is 30, so LXT, X is the current age 30, and then T is the period, in this case, 20 years. And in this question, it is denoted L20. All right, L20 follows a binomial distribution with L30 and probability parameter 20p30. We need to get 20p30. By definition, and we get 20p30 is 0.881475. And we have L30, 5,000. And therefore, L20 follows a binomial distribution with parameter 5,000 and probability 0.8814. From that, we can get the expected value and the variance. That's it for today's video. Thank you for watching. In the next video, we will be covering fractional ages. See you in the next video.